the software industrial revolution has arrived. Software used to be built, proprietary, and now it's more assembled than it is built, really. It's maybe 20% custom software that performs individual business functions, and it's sitting on a substrate of 80% of third-party dependencies and libraries that provide common behavior and operationalization for those particular units of work. And what that's led to really is this explosion in the ability to develop new experiences for customers, new business critical functionality to innovate faster than ever. This is actually a hidden infographic back for one organization we were talking to not too long ago. In both 1997 and 2014, they had around 40 repositories, source code repositories, and 70 engineers. And today, they still have 70 engineers, but have 900 source repositories. So you've got this 25 times explosion in the amount of software or custom software inside the organization. The team has delivered new experiences, has delivered a whole new product line, has expanded to other parts of the country, but don't have any more engineers working. They just have 25 times the amount of code. So if any given repository requires a certain level of maintenance and upkeep just to keep it working and running smoothly, then a 25 times growth in your total code base means really a 25 times growth in that maintenance activity as well. And as we talked to various organizations, we found different ways of measuring this, but it seems like it's about 30% of engineering time these days are spent doing that, keeping the lights on maintenance activity, really, that's necessary. After all, these third-party libraries and dependencies evolve at their own pace, independent of your business and your customers' needs. And not keeping up leads to critical bugs and failures and security vulnerabilities and so forth. So it's as important as ever as it is to keep it up to date. One thing we've also noticed is that maintenance activities are highly repeatable, really. And that's not surprising. After all, if our code base is 80% third party, there's going to be a lot of commonality in the components that we use across industries, across company sizes, and so forth. And so the activities are actually be very similar. And wherever you find a high degree of repeatability in some sort of effort, there's an implication that the activity is ripe for automation. And I do think that software maintenance, the actual tedious work necessary to keep things running, is at a point now where automation is necessary to manage the sizes of code bases that we have. So, just myself, I started working on automatic refactoring at Netflix back in 2016 as part of the engineering tools team. But then, moved on and got to experience the software engineering organizations of a lot of different types of industries, working for the Spring team at Pivotal. And these days I have, with the folks I've worked with in the past, have started a new company really around this auto remediation. And it's based on an open source technology called OpenRewrite, which is really forked from the original Netflix code base. And we're going to see that today and how you can write recipes to automatically fix code in a style preserving way. And then there's also a platform around that that runs those recipes at scale on up to hundreds of millions of lines of code. And so as we I want to go at this from sort of outside in and show you, first of all, the platform and how we can take a recipe and run it across, a lot of code and the kind of experience that creates. But then don't want to focus too much time on that. And instead, we'll go over and actually write a recipe and see what that looks like and what that activity could look like. Because I know this is a very new field, really. So first of all, this company is called Modern, and we address software maintenance automatically. And again, we're leveraging OpenRewrite. So what you see here in this graphic is really just one change to a Spring Boot application that was previously on Spring Boot 1 and needed to move to Spring Boot 2. And the library has had some underlying change, or that a breaking change that you had to take, in this case, this conditional on being, and split it into a separate class that implements any nested condition. And this same kind of change would occur anywhere that functionality was used. So one characteristic of what we're going to see with these recipes as they make suggested changes to code bases is that it's really important that they preserve the original style of the code base. So we may run this on 10 repositories or 100 or 1,000, and there could be substantial variation in the white space rules and import ordering and these sorts of things that seem like trivialities, but are very important to us as software engineers working on individual projects. We like to see that consistency. So these recipes are really are good at actually maintaining that style. I'm going to flip over now actually to the platform, and let's just start with something. We're going to run one recipe on our own code base, our own OpenRewrite code base, and see what happens. So over here, what we see is the Modern platform, and this is a catalog, a tree view of recipes that are available all in open source. And they span, we can automatically fix Terraform or Kubernetes or Java, and a heavy emphasis on Java right now. And let's go into just the cleanup category of Java and look at common static analysis issues. So one characteristic of recipes is that recipes, as a unit of transformation, say, I want to fix all common static analysis issues in my project. Recipes can actually depend on other recipes. And so you can, just like any form of encapsulation, you can build up a higher and higher order functionality by assembling components together. In this case, common static analysis issues depends on a bunch of individual recipes that do different things, like looking for covariant equals or explicit initialization. And these are actually associated to, in this case, SonarQube issues that, you may have something like this running in your environment. SonarQube, of course, just reports issues. We've been looking at a lot of these rules provided by common static analysis tools and, reproducing the experience of finding violations, but at the same time also automatically fixing them or providing an automatic fix for them. So it's just kind of the next evolution in what it means to build this kind of code intelligence. So I've pre-selected the 21 repositories of OpenRewrite organization, and we'll take we'll actually have assembled a few other things here in a custom recipe that that I've created, and we're going to run this on those 21 repositories. So what we're operating on here is actually a sort of pre-compiled representation of the code in abstract syntax tree form. We'll talk more about that in a little bit, but it allows us to run a recipe very quickly on up to hundreds of millions of lines of code and see that result very quickly. So here's some of the repositories where, some of them there are no results found at all, and some of them require some cleanup. So kind of clicking into one of them, you'll see, the typical kind of static analysis issue that might be found. This one isn't super interesting, I know, but just that as field access.getSimpleName could have returned a null. And so if it's on the left side of this dot equals, then that could lead to a null pointer exception. So if we flip the literal to the front, then it no longer can create an MPE. So we've just sort of eliminated a class of potential bug here. And there's going to be similar results on other repositories. In this case, we found a field that had a default value that really, it's implicitly false if you don't say anything. So we can just clean this up a little bit. And so here's, I think we've found about so far 8 repositories of changes to make. And so as a contributor on this project, I can just say commit all 8 of these results. And we wait for GitHub for a little bit here. So what the platform is actually doing is cloning each one of these 8 repositories, taking the results that OpenRewrite has suggested and applying them to those repository on disk. then committing the end result. So it committed all 8 successfully. And if I click into one of them, what we see is actually the change that we saw in the platform there with the actual change made. And note the actual author here is me. It's Johnathan. I'm the one that ran the recipe. I controlled this process. I reviewed it. And so I'm responsible ultimately for the result here. But what it did make me is very efficient. I just fixed all the static analysis issues across 8 repositories. And in the process, it says saved, roughly 2 hours of time, according to SonarQube's estimate, or 23 hours if we include this last repository just popped in. And I'm done, right? I've just done that very effectively and kind of move on. That's kind of exciting, so you could kind of sense, I hope you're developing a sense that the changes actually can be very small things like, inverting the order of things, or they can be very structural changes. There's a lot of possibilities here. So how does this work? Like maybe just a little bit more about the actual data model itself. And I'll flip back to the slide. So if we're going to build this kind of source code automation, we need a lot of intelligence about the code itself. And not surprisingly, we're starting with the text version of the code and we're turning it into an abstract syntax tree. But this abstract syntax tree of OpenRewrite is special. It includes all the formatting of the original code, all the type attribution, all the stuff the compiler knew about as it was, downloading dependencies or, applying dependencies and compiling. So ultimately, the data model is super rich. It's not just, we're not doing text search. We're not doing syntactic analysis. We're doing a form of analysis that involves the syntax, the types, the formatting, dependencies, Java version, environment variables that came into this build. All sorts of things are kind of being mixed in this rich stew that gives us the ability to perform these changes in a style-preserving and accurate manner. We actually render, this is a file from the Spring Cloud project, one of the Spring Cloud projects. We tried to actually render every piece of metadata that OpenRewrite puts on the tree, and had to omit 600,000 nodes that we just couldn't somehow stuff into this representation and get to render on a laptop. So, and idea here, I guess, just it feels very magical what these recipes are doing, but behind the scenes is just a lot of hard work and a lot of data. So pretty cool. I think it'd be fun to actually write a recipe and kind of get a sense of what that looks like. So that, because, as we work with many organizations, both, with open source and with as a company, a lot of organizations write custom recipes. They have internal platforms, platform libraries and APIs, and it's just as important to maintain those as it is to maintain third-party open source dependencies and libraries as well. So I'll flip over to IntelliJ, and we'll try to write something that's that expresses some of the capability. So here we're going to rewind some of this here. We've all kind of encountered this log for shell thing now, right? That logging statements can be an issue, and it'd be one thing to try to write a recipe. We can write recipes to actually manipulate dependencies themselves, but what if we just went and, one just kind of like joke here would be to look for all logging statements and just replace them with runtime exceptions, because then you can't be vulnerable to remote code execution if your code is crashing. So I guess that's the joke, but at least it'll show some of this capability. So here we've really just noticed, first of all, that this is a class. We're going to say blame the boss, and you'll see why in a moment. But it's a program, really. A recipe in OpenRewrite is not a query. It's not a SQL-like query. It's not a query language. It's actually a program, and those programs run in a very horizontally scalable manner as needed. So, we're going to do a visit over code. We're going to navigate the abstract syntax tree of this code, and we're going to do some things here. So let's get a method matcher for like log4j. We're going to look for method like log4j type methods. I think we've got some similar method matchers probably already if we look in the right place. So we've got a recipe is actually just a program. It's not a query. It's not a SQLite query. It's actually a program that runs in a horizontally scalable manner across these abstract syntax trees. So that's the first thing to note. And so then the expressive power of what you can do with the recipe is really kind of based on what you can do in a program. So it's very, it's highly capable in that sense. We're going to need to look for logging statements if we want to replace them. So we can use something called a method matcher, which in this case, we're going to look for any implementation of category with any method name, that's the star, and an object in any, or really just any parameters probably would be fine here. And if we look at, we could create a visitor, and a visitor is just going to navigate down the actual abstract syntax tree and look for things. And I'm going to visit method invocations. So these are actual calls to methods. And I'm going to say if log dot matches method. So I don't really need to know how to parse apart the method invocation itself. We can just match on this matcher up here. Then what we want to do is like take a log.info, something like this, and replace it with, we're going to say runtime exception, because, my boss told me to, or something. That we don't want remote code execution, this kind of thing. Again, kind of a bit of a joke here. But so we're going to replace this with something that looks very different. And I don't want to build up the abstract syntax tree of this new statement and this literal and this throw. And so we can use something called Java template in this case. And Java template allows us to build code snippets and then inject them into the AST in certain places. And so we're going to get the current cursor here. This needs to be down here, actually. And so we're going to build a code snippet that says throw new runtime exception. And actually, recipes can take parameters, and we'll see what that looks like in a moment. But let's say, because somebody, and we'll use this as a parameter, told me to. And so here, to replace the log, the log statement with a thrown exception, we could say method.withTemplate, and our template is the exception that we want to use. And we're saying, I'm going to get the coordinates of this method, and I'm just going to say, I just want to replace the whole thing. And my parameter, let's go define a parameter here. We can say option. Recipes can have options. Let's say our manager's name. And we'll make this a string here. So I can use this down here, manager name. And that's it. I just have to return this. So this can be final. And that really is the recipe. Let's look at what it means to test something like this. So here, I've written the recipe here. I want to test it. We have a whole unit testing harness around this. I've got the before, I've got the after sort of pre-written here. And so, there's a lot of detail here, but we construct a Java parser to actually parse the code itself. And you can see that even in this unit test here, this is syntax highlighted. And I'm saying, I want to use my new blame the boss recipe, and my manager's name is John. And what did I use for the text over here? I said, because John told me to, is what, So we can replace this here. And so I should be finding this logger.fatal and replacing it with this runtime exception. And that passes. So that's the technique. So you can imagine just creating these unit tests for various different circumstances that would occur in real code. And again, because of, we put a lot of work into making sure that the IDE even provides completion hints inside of the tests that you're writing, even though those tests are strings. So you can really go and kind of go crazy with this, actually testing it and making it really effective. So I've actually taken this, just like any good cooking show where they've baked something in advance. I've taken this recipe here and built it into an artifact and deployed that over on the platform we showed earlier. And so let's just run this, across a bunch of different things. It showed up in this logging category over here, where we called it, I think at that time, eliminate the possibility of remote code execution. And I'm just going to run this on absolutely everything that we have and say, my name's John. Let's see, my manager's name is Johnathan. And so you notice that the recipe option that we included over here actually just showed up as a dynamic form over here on the platform. And when we run it, we'll just get to see what that does, to code bases. So maybe we'll filter this here, just looking for things that we actually find, and just ignore everything else. And yeah, sure enough, I had this logger.info and now I'm throwing a runtime exception instead. So obviously you would want to build a much more sophisticated recipe on the end, but using these kind of tools that we built around templating and matching and finding, and there's so much you can do to build really sophisticated things very quickly. And yeah, just maybe show something different, outside of the Java world. Let's look at something like Maven. And this really excites me, this idea of being able to manage dependencies in this way. Like Jackson, we know in the Java community has always been tough on us maintenance-wise because, and for no fault of their own, there's often deserialization gadget vulnerabilities that are found in Jackson. And the author has been fantastic about going back to old minor releases and releasing patches to fix that vulnerability over time. But it's also the kind of library where if you have half of the application running on one minor version like 2.10 and one running on 2.9, you're in trouble. So we have added things like version constraints don't actually exist in Maven or Gradle, called latest.patch, that knows how to look for something and determine whether there's already whether there's a later version that's in the same minor release but is of a later patch version. I think that's really exciting too, to be able to kind of cater the actual dependency fix to each repository, meeting it where it is. So if we click into any one of the results here, we'll just see what we find. And yeah, you see this one here used, Jackson 2.11, and we pulled it from 2.11.1 to 2.11.4. And, here, this one was back on 2.8. So the real fix is to pull it up to 2.8.11. So that it could be manipulating a property. You could have to manipulate a dependency management section or inline it, or there's all sorts of variation on what it means to pull something forward. But that's something that we can progressively encapsulate into what it means to upgrade a Maven dependency, all that tribal knowledge that our developer tools people especially have, and that, the typical product engineer doesn't have as much, and use it and deploy that knowledge across, the code base at large. So it's super exciting. The world that I would love to see evolve here is one where actual framework authors, if you're the maintainer of Kubernetes, or you're the maintainer of Spring Boot, or you're the maintainer of Micronaut, that you would, when you make breaking changes, that you would provide recipes and open source that would help your users move forward. And one team that's done a really great job of this is actually the Micronaut team at Oracle. If you look at their latest guide, they did a major release recently to 3.x from their 2.x line, and did a lot of the work necessary to write recipes such that you could just apply this recipe to a code base that was on Micronaut 2 and just run on it with the build tool locally. And that repository would have been migrated forward to Micronaut 3 largely. What a world we would be in if every vendor or vendors really took responsibility when they made breaking API changes to do the little work necessary to provide the recipe downstream of them. And these things really have a stacking effect. So if we look at say like in the testing world, we look at JUnit Jupyter and what it means to go from JUnit 4 to JUnit 5. That recipe, you don't only have to deal with JUnit things, but you also have to upgrade, Mockito 1 to 3. You have to deal with Hamcrest assertions. You have to deal with Mock Web Server and OKHTTP. So a lot of these sort of changes are stitched together. So if you're a library author out there, I challenge you to start thinking in this way: is what can you do to help your user base move forward and get better? I really appreciate you taking the time to join our conference today, and look forward to engaging with you further. Thank you.